Today we are going to learn about the blood pressure. What is blood pressure? Blood pressure is actually the pressure of blood against the wall of the blood vessels, and how this blood pressure is regulated. We will learn about this in this lecture, in today's lecture. In the diagram you can see this is a complex diagram in which we will come to this diagram at the end. In the start we will come to this diagram. Focus on this diagram. In this diagram you can see a heart represented by blue color. From the heart aorta arises. This is aorta. This is the main artery which arises from the left ventricle. You can also see here these are the aortic walls. This is the aortic wall made up of three flaps. Aortic wall. This one and this one, these two are nodes. This is SA node and this is AV node. This is the ascending aorta. This is the aortic arc, and this is the descending aorta. Now coming towards this one, from the aortic arc, this is brachiocephalic artery. The brachiocephalic artery further gave right brachial artery and common carotid artery. Further it gave internal common carotid artery and external common carotid artery. Now coming towards this one, this is the common carotid artery, left common carotid artery. This also gives external common carotid artery and internal common carotid artery. And this one, which we have learned previously, this is the left brachiocephalic artery, left brachial artery, not brachiocephalic. Achha. Now coming towards the next diagram, this one. In this diagram you can see a heart. This is heart and represented in blue color. This is aorta. You can see in the ascending aorta, this is the aortic wall. This is the aortic wall, but near the near the aortic wall, you can see that the blood vessel or the artery or the ascending aorta is a bit flattened. This is dilated. This part of the aorta is dilated. This part of the aorta is dilated. This is the ascending aorta, and in the ascending aorta, near the aortic wall or near the wall of the ascending aorta, the blood vessel is a bit dilated. This is normally in dilated form, or this is just like a cavity. This represents just like a cavity. So this dilated portion of ascending aorta, this is called aortic sinus. This is called aortic sinus. This one and this one. This is the aortic sinus. This part of the aorta is dilated. This is called aortic sinus. Aortic sinus. Now further, this is the internal common carotid artery. This is the internal common carotid artery. This is also the internal common carotid artery. This is the left common carotid artery, and this is the right common carotid artery. And this common carotid artery, you can see that this portion near the junction, this portion, this is also a bit dilated. This area and this area a bit dilated. This is the flattened part of the internal common carotid artery. So this is called, these two areas are called carotid sinus. Carotid sinus. Aortic sinus, which was present on the aorta, and the carotid sinus, which is present on the carotid artery, internal common carotid artery. Now further, you can also see in this diagram over here small dots. Over here small dots, and over here also small dots are present. Small dots are present near or on the aortic sinus, on the aortic arc over here, and on the carotid sinus. Small dots are present. Small receptors are present. These are actually receptors. I have made these receptors are invisible, but I have made it for you people to make you understand. So these are what are these? These are actually these are baroreceptors. The baroreceptors are present on the aortic wall, on the aortic sinus. Baroreceptors are present on the aortic arc and on the carotid sinus. Baroreceptor. These are baroreceptor. Baroreceptors. Baro mean pressure and receptor mean receptor. Regarding the receptor, you will learn about this receptor in pharmacology, and I have already explained the receptor. Next one. But I have told you that these receptors are invisible. These receptors are baroreceptors are invisible. You can't see these baroreceptor. If you have a heart of an animal or human, you can't see these receptors. These are invisible. And now the next diagram. Focus on this diagram now. Near the aortic sinus, you can see these are receptors. These are baroreceptor, but these are some bodies. These are some bodies which is represented in which color? In the green color. These are bodies. And similarly, also some bodies are present over here on the carotid sinus, and aortic sinus. But also apart from the sinus, over here also this is present. So these bodies are called aortic bodies, and which are present on the common carotid artery, or the internal common carotid artery, are called carotid bodies. The bodies which are present, small bodies which are present on the on the aortic sinus or on the aorta, these are called aortic bodies, and the bodies which are present on the carotid sinus are called carotid bodies. Simply you will add the word bodies, carotid and aortic. The bodies which are present on aorta are called aortic bodies, and the bodies which are present on the common carotid artery are called carotid bodies. But you will learn about the carotid bodies and aortic bodies later, but simply you will remember a few words about the common carotid, about the aortic or carotid bodies, that these bodies are visible. These are visible. These are having 3 to 5 millimeter 3 to 5 millimeter size, and these are also having 12 milligram weight. You can see it by your eyes. So these are visible. These are small bodies. That is why these are called bodies: common aortic bodies and carotid bodies. Achha, the aortic bodies and carotid bodies contain small receptor, large number of small receptors. Just like I have made some receptors over here, but these are baroreceptors. But on the aortic bodies, small receptors are a large number of small receptors are there, and those receptors are called chemoreceptors. Chemoreceptors. So where are the chemoreceptors available? Where are the chemoreceptors present? Chemoreceptors are present on the aortic bodies and carotid bodies. On the carotid bodies and aortic bodies which are present, chemoreceptors are present. Large number of invisible small receptors are present. These are these are chemoreceptor. Now what is the function of chemoreceptors? Chemoreceptor actually detect chemoreceptors. I want to make these. Chemoreceptors are responsible for the detection of CO2, proton and O2 concentration. Not like this. O2. The chemoreceptors. The chemoreceptors are responsible for the detection of carbon dioxide, hydrogen ion, and oxygen concentration in the blood. These are responsible for the detection. Chemoreceptors are responsible for the detection of these three chemicals, these three entities, for the detection of oxygen, proton, and carbon dioxide concentration in the blood. The chemoreceptor, or you can also say that the carotid bodies and the aortic bodies are responsible for the detection of carbon dioxide, proton, and oxygen concentration inside the blood. Inside the blood. These carotid bodies and aortic bodies are also having blood supply. Yes, there are veins and arteries which supply blood to these bodies. So during the blood supply, these detect the concentration of carbon dioxide, proton, and oxygen in the blood. So these are chemoreceptors. These are for the detection of chemical. These three chemicals. Now, what is the function of baroreceptor? The baroreceptor detect the pressure. The baroreceptor detect the pressure of blood against the wall of the blood vessels. Actually, a large number of baroreceptors are present on the sinus, on this sinus and this sinus, not this one, on this sinus and this sinus. So this sinus is easy to be dilated, easy to be flattened. So the aortic bodies, these receptors, the baroreceptor, are responsible for the detection of pressure of blood against the wall of the blood vessels over here. Now, coming toward the next diagram, as I have told you that the baroreceptor and the chemoreceptor are present in aortic and carotid bodies. The baroreceptor and chemoreceptors detect the blood pressure and the concentration of carbon dioxide and oxygen and proton. These, after detection of blood pressure, for example, let's suppose we are talking about the baroreceptor. When the baroreceptor detect the blood pressure, this detection of blood pressure is communicated with the brain, with a nucleus. This is a nucleus, and the brain, in the pons area of the brain, in the pons that is present in the brain stem. So in the pons there is a nucleus. In the pons there is a nucleus. This nucleus is called Tractus Solitarius. This nucleus is called Tractus Solitarius. This Tractus Solitarius is responsible for the detection of what? For the reception of the impulses from these bodies. This Tractus Solitarius is responsible for the reception of these signals from this area and from lower area to this. The neurons are the fibers. Neuronal fibers are neurons which are responsible for the passage of these signal, for the passage of this action potential from these bodies to Tractus Solitarius, are having different name. This one, the neuron which transfer the impulses, which transfer the signal from these bodies, from the baroreceptor or the chemoreceptor of this sinus, of the carotid sinus, to Tractus Solitarius. This neuron is actually glossopharyngeal nerve. Glossopharyngeal nerve. Glossopharyngeal nerve. Glossopharyngeal nerve. Nerve number 9. This nerve, this is cranial nerve number 9. This nerve transmit the signal from baroreceptor or chemoreceptor of the carotid bodies to the Tractus Solitarius. Now this one, this nerve fiber, these neuron, these afferent neuron transmit the signal from these bodies, from the carotid bodies or from baroreceptor of the carotid sinus to the Tractus Solitarius. These neuron are called which neuron? Vagal nerve. Vagal nerve. You can also call it vagus nerve. Vagus nerve or vagal nerve. Both are same. So these these signal are transmitted from the baroreceptor and chemoreceptor to the Tractus Solitarius. Now coming toward the next diagram. In this diagram you can see the receptor. This is the nucleus Tractus Solitarius, which receive from the carotid bodies and aortic bodies, from carotid sinus and aortic sinus, which receive the signal. This is called Tractus Solitarius. Now you can also see 4 nucleuses over here. 4 nucleuses over here, and these 4 nucleuses are combinedly called as cardiovascular center. These 4 nucleuses combinedly make the cardiovascular center. This cardiovascular center is present in the medulla. Some part of this is also present in the pons, but this is actually, you will write it here that this is present in the medulla oblongata. So these 4 nucleuses combinedly make what? These 4 nucleuses combinedly make the cardiovascular center, which is present in the medulla oblongata. The cardiac center, which is represented in red color, this one, this is called combinedly these 4 nucleuses are called cardiovascular center, but this red one is called, these 2 red nucleuses are called cardiac center, and this blue nucleus, these blue nucleuses are called vasomotor center. Vasomotor center. These 2 nucleus make vasomotor center, and these 2 nucleus make cardiac center. So the combination of vasomotor center and cardiac center make the cardiovascular center of the medulla oblongata. So when the signal come from carotid bodies, from carotid area or aortic area, or also come from the aortic arc, these signals are transmitted to Tractus Solitarius. After transmission to Tractus Solitarius, these are communicated with this cardiac center, cardiovascular center. Now coming toward the next diagram. In this diagram, you can see that the signal which come from carotid or aortic area, these are communicated with the Tractus Solitarius, and Tractus Solitarius transmit the information to the cardiovascular center, to this center or this center, both. Now I also want to explain a few words about this cardiovascular center, but it will require your attention. This cardiovascular center composed of 2 nucleuses. This nucleus, which is in proximity with the Tractus Solitarius, this is called CIC, cardiac center. I want to make it a bit clear. CIC. And this one is called CAC. This is called cardio inhibitory center, and this is called cardio acceleratory center or cardio activatory center. This is called cardio-inhibitory center, and this is cardio-activatory center. Cardio-inhibitory center, CIC, represent the cardio-inhibitory center. This is the cardio-inhibitory center. This one is cardio-inhibitory center, CIC, and this one is CAC. This is cardio-activatory center. Cardio-activatory center. Now focus on this diagram. In this diagram, you can see two nucleus. This nucleus, this is called vasoconstrictive center. Vasoconstrictive center. And the other is called vasoconstrictor center, and vasoconstrictor center, and vasodilator center. Vasoconstrictor center and vasodilator center. This one is vasoconstrictor center, which is near this one, and this is vasodilator center. So the combination of CIC, CAC, vasoconstrictor, and vasodilator center make the cardiovascular center. So what is the function of these center? The CIC is responsible for the what does its name represent? What does the name represent? A CIC, cardio-inhibitory center. This is responsible for the inhibition of heart. Cardio-inhibitory center. This is responsible for the activation of heart. It decreases the heart rate. Inhibition, no? This increases the heart rate, right? This is vasoconstrictor center. This constrict the blood vessel. This is vasodilator center. This dilate the blood vessels. So when and in which condition these nucleuses will be activated, which will be known in next diagram. First focus on this diagram once again. When, if for example, the blood pressure is high, the carotid and aortic sinus are dilated. When the carotid and aortic sinus are dilated and blood pressure is high, the baroreceptor, or when the carbon dioxide concentration is enhanced, the not carbon dioxide, that will be learned further and later. When the blood pressure is high, the carotid and aortic sinus are dilated. These carotid sinus and aortic sinus, after dilation, stimulate the vagal neuron and glossopharyngeal neuron. This vagal neuron and glossopharyngeal neuron transmit the signal to Tractus Solitarius. Actually, the blood pressure is increased, and this increase in blood pressure is detected by these receptors, and this increase in blood pressure is transmitted to this information of increase in blood pressure is transmitted to the Tractus Solitarius. Now the Tractus Solitarius is very wise nucleus. This actually this can differentiate between the signals of the high blood pressure and signals of the low blood pressure. So if the signal if it detects the signal of high blood pressure, so it will do two things. Blood pressure is high, so it will first of all it will stimulate this nucleus. Which nucleus? This nucleus. And this nucleus this is CIC, this is cardio-inhibitory center. This nucleus, when this nucleus get activated, what will happen? This will transmit the signal. And this will transmit the signal towards the heart. Now this Tractus Solitarius will also inform this vasomotor center. In the vasomotor center, it will give information to which nucleus? Actually, the blood pressure is high. So it will give information to the vasodilator center. This nucleus, to dilate the blood vessel. When the blood vessel is dilated, the blood pressure will automatically become low. Now what will happen? Coming toward the next diagram, for example, focus on this diagram now. Your attention is required at this moment. This Tractus Solitarius, for example, the blood pressure is high, and this Tractus Solitarius transmit the information to this nucleus, cardio-inhibitory nucleus, cardio-inhibitory center. So this cardio-inhibitory center, when this get activated, this will transmit the information directly. This will transmit the information directly towards the heart. This will transmit the information directly towards the heart, towards the SA node and AV node. This is AV node and this is SA node. Focus just on the red line, on the red representation. This one. The cardio-inhibitory center is activated, and this has transmitted the information toward the SA node and AV node. On the SA node, two types of receptors are there. On SA node, this cardio-inhibitory center will activate the M2 receptor. This is M2 receptor. This is also M2 receptor. This is M2 receptor. This is M2 receptor. This cardio-inhibitory center will activate the M2 receptor. After activation of M2 receptor, the M2 receptor is responsible for the M2 receptor. यहाँ पे हम थोड़ा सा देख लेते हैं. M2 receptors. What is M2 receptor responsible for? This is actually cholinergic receptor, and this is responsible for decrease of heart rate. This actually decreases the heart rate. The normal I have already told you in the previous lecture that SA node is responsible for the phase making. This is responsible for the generation of signal. It normally generate the signal of 100 beats per minute. The SA node is responsible for the detection of the generation of 100 beats per minute. SA node. This is the normal. This is the normal phase of the SA node. But if the blood pressure is become high, and the heart rate, usually the blood pressure become high due to increase of the heart rate. Due to increase of the heart rate, the blood pressure become high. So by transmitting the signal towards the CIC transmit the signal towards the M2 receptor of the SA node and M2 receptor of the AV node. And so it decreases the signal generation of the SA node and AV node. It decreases the signal generation of the SA node and AV node. So when it decreases the signal generation, the heart rate is decreased. Automatically the heart rate will be decreased. The heart rate depend upon the signal generation of SA node and AV node. If the SA node generate the signal a bit low, if the speed of the signal generation is slow, so it will this SA node normally generate 100 beats per minute, generate signal for 100 beats per minute, but this CIC maintain the 75 or 72. It continuously 72 beats per minute. It continuously inhibit the SA node and AV node to decrease the heart rate, to decrease the signal generation. The SA node continuously make 100 beats per minute, create the signal for 100 beats per minute, but the 20 or 25 beats are erased by this nucleus. This nucleus do not allow this SA node to make more heartbeat, to make more signals. So this is the cardio-inhibitory center. But if sometimes the cardio-inhibitory center activate these M2 receptor. When these M2 receptors are activated, it will automatically lower the heart rate, and when the heart rate is decreased, the blood pressure will eventually decrease. So this is one feedback mechanism. Another feedback mechanism, for example, you can also call it this one. This is the parasympathetic nucleus. This is the parasympathetic nucleus and this is the parasympathetic pathway. This is the parasympathetic pathway for what? For the decrease of heart rate, to decrease the heart rate. This only decrease the heart rate. This can only decrease the heart rate. This can't do anything else. Now, for example, the heart rate is increased. Then the baroreceptor and chemoreceptor have transmitted the signal towards the Tractus Solitarius. The Tractus Solitarius will transmit the information towards this one. The blood pressure is decreased, no? If the blood pressure is decreased, it will transmit information toward the cardioactivatory center. The cardioactivatory center will, this is actually the sympathetic nucleus. This will transmit the information toward the spinal cord. And in the spinal cord, in the thoracic area, this will transmit the information toward the interneuron. And from the interneuron, this will transmit the information towards this SA node and AV node. The SA node and AV node. The SA node and AV node. What will SA node and AV node do? The SA node and AV node will contain those beta 1 receptor over here and beta 1 receptor over here. Beta 1 receptor is also present on the in the muscles of the heart. So this will the sympathetic pathway will stimulate the beta 1 receptor over here, the beta 1 receptor on the AV node and the beta 1 receptor on the cardiac muscles. So when this nucleus, this cardioactivatory center is activated, this will transmit the information towards the SA node, AV node and the cardiac muscle. By transmitting the information toward the SA node, AV node and cardiac muscle, this will increase the heart rate. Now coming toward the next diagram. In this diagram, in the previous diagram, we have learned about this one. This is also sympathetic pathway. This will also activate this one. This is actually what is this? This is actually adrenal gland. This is also activate the adrenal gland to secrete the epinephrine or adrenaline. So this adrenaline will go to the bloodstream and that will eventually increase the blood pressure. Now this one, for example, this nucleus get the signal of high blood pressure. So this will activate this one, the vasodilator center, and the vasodilator center will transmit the information over here. To transmit the information towards the veins. These are veins. I have made the veins in which walls are there. The veins always contain walls, and the arteries do not contain wall inside the lumen. So the veins and arteries contain alpha receptors. These are alpha receptors. So the alpha receptor will be activated when the blood pressure become high. This will transmit the information toward this nucleus, the vasodilator nucleus of the vasomotor center, and the vasodilator nucleus will transmit the information toward the veins and arteries, all the veins and arteries of the body. And these arteries and veins contain the alpha receptor. These alpha receptor what will it do? It will decrease the blood pressure. How will it decrease the blood pressure? It will dilate the blood vessel. When the blood vessel is dilated, what will happen? After dilation of blood vessel, the blood pressure will be decreased. But if the blood pressure is low, if it detects the low blood pressure, this lowering of blood pressure will be transmitted toward this signal will transmitted toward this one, and this vasoconstrictor center will transmit the information toward these alpha receptor, and these alpha receptor will constrict the blood vessel. After constricting the blood vessel, the blood pressure will eventually become high. Now apply this formula also on the chemoreceptor. When the chemoreceptor when the concentration of carbon dioxide or hydrogen ion become high in the concentration of hydrogen or carbon dioxide become high inside the blood vessel, these these chemoreceptor, these carotid bodies and aortic bodies, the chemoreceptor which are present on these bodies transmit the signal towards this Tractus Solitarius, and what will it do? It will increase the heart rate. It will increase the heart rate, and it will also constrict the blood vessel. So by increasing the heart rate, it will pump more and more oxygen, more and more blood towards the lungs to get the blood oxygenated. So the same the increase of carbon dioxide and increase in hydrogen level activate this cardiac center, activate this Tractus Solitarius, which transmit the signal toward these both nucleuses, and these nucleus eventually increase the heart rate. When the carbon dioxide and hydrogen level is increased, the heart rate will be increased. When the carbon dioxide and hydrogen level is decreased, the heart rate will be decreased. A similar phenomena for the oxygen. When the oxygen concentration in the blood is increased, the heart rate will be decreased, and this is and following this this pathway, the heart rate and the blood pressure will be decreased. One more thing you should keep in mind, that the blood pressure is also regulated by the limbic system, the hypothalamus. Hypothalamus is the center of our autonomic nervous system. So the blood pressure is also regulated by the limbic system, or the cerebral cortex also. So sometime due to fluctuation in the emotions of the body, the emotions of the brain, the blood pressure become high or low, and that also following the same pathway. If the emotions, if you get some emotion fluctuation, that will transmit the information toward the cardiovascular center and vasoconstriction center, that will normally increase the blood pressure, and after increasing the blood pressure, again the feedback mechanism will be generated over here. And I think for today this was sufficient.